Operation Hardtack 1958 encompassed a greater variety of military effects studies than any previous nuclear test series, necessitating the division of the Defense Atomic Support Agency's review of the effects results into 4 films. Part 1 covers basic effects, particularly of megaton devices, and effects on material and structures. Part 2 describes the effects results for the 3 high-altitude shots. Part 3 is devoted to the effects results for underwater tests. Part 4 reviews the effects of sub-kiloton detonations. Today's increasing international emphasis on long-range ballistic missile activity raises to priority attention the mastering of high-altitude burst effects phenomenology. At stake are urgent problems, such as those associated with ICBM defense, as well as the upper air burst effects on radio communications and radar. Prior to 1958, only 2 nuclear shots had been fired at altitudes above 10,000 feet. Both comparatively low in height, both of small yield. The first was in 1955, a 3-kiloton airdrop during Operation Teapot, with height of burst at 36,000 feet above mean sea level. The other occurred in 1957 during Plum Bob. On Hardtack, 3 high-altitude shots were fired to acquire data necessary to develop a national capability for high-altitude warfare. Yucca, a 1.7 kiloton device suspended from a balloon, and Teak and Orange, both 3.8 megaton devices carried by Redstone missiles. All were fired to obtain effects data for the fulfillment of 3 general objectives. First, to find out how extreme altitudes affect the partition of energy in a nuclear detonation, and what is the radial extent of the various phenomena. Second, to determine scaling laws for various effects as a function of altitude and yield. Third, to determine the effects of high-altitude bursts on the ionosphere and on the propagation of radio and radar signals. To gain these objectives, specific effects tests were carried out to provide a basis for a theoretical understanding of the phenomenology of high-altitude bursts. Yucca, the first of the 3 high-altitude shots, was prepared and launched from the flight deck of the aircraft carrier USS Boxer. All of Yucca's blast and nuclear radiation instrumentation and a portion of the thermal instrumentation were concentrated in 5 canisters suspended below the weapon at intervals out to 3,000 feet. These instruments were designed to be activated prior to burst time by telemetered commands. Additional instrumentation was carried by 3 aircraft. 2 were modified B-36s, positioned at 40,000 feet altitude, 12 miles from the detonation, to obtain fireball photography and thermal data. The 3rd aircraft was a P-2V 15 miles from the burst point at 22,000 feet. This aircraft measured infrared phenomena. At 1125 hours on 28 April, when the Yucca balloon was released, the USS Boxer was operating about 90 nautical miles northeast of Nan Island, Bikini Atoll, maintaining a deck wind velocity of near 0. 2.5 hours later, 1440 hours, at an approximate altitude of 85,000 feet, Yucca was detonated by radio command signal. Failure of the telemeter command transmitter to activate the canister instruments prior to burst time resulted in almost complete loss of data from the balloon dragline equipment. The aircraft-mounted instrumentation provided excellent data. Here is a rundown on the results of the Fireball studies. Yucca produced a bright fireball with a center core, which rapidly developed into a toroid similar to the teapot and plumb bob altitude shots. The major part of the thermal pulse lasted about 30 milliseconds, with some perceptible signal for as long as 500 milliseconds. A double maximum was observed in the first part of the pulse, followed by a minimum at 2 milliseconds, then a second maximum at about 13 milliseconds. High-speed spectrograph recordings were made. These showed that during the first 100 microseconds, there were definite discrete absorption spectra in the continuum. Between 100 microseconds and 2 milliseconds, the spectrum was essentially continuous with little or no discrete structure. As the intensity began to rise beyond the minimum, there was a marked appearance of discrete absorption, continuing to just beyond the maximum at 13 milliseconds. After waning, the discrete absorption was replaced by discrete emission lines or bands, which persisted for the remainder of the bomb pulse. As for Yucca results in the infrared tests, instrumentation aboard the P-2V showed no observable infrared emission. The Teak and Orange missile shots were fired from Johnston Island, about 720 nautical miles southwest of Honolulu. Experimental arrays on Johnston for these two shots were essentially identical. Project stations were crammed on Johnson and Sand Islands, supplemented by other stations in Hawaii, in aircraft and on shipboard. Each device was sent aloft by an Army Redstone missile. Attached to each missile were 4 pods, released during the acceleration phase of the Redstone. 3 of the pods contained telemeter-equipped instrumentation for the nuclear program. The 4th pod, programmed to be closest to the detonation, was utilized primarily for studying the vulnerability of ICBM structural materials, with particular emphasis on X-ray effects. In addition, neutron flux and energy spectra were investigated by use of neutron activation and fission foils. The first of the 2 missile shots, Teak, was launched on 1 August. It was planned to detonate at 250,000 feet, approximately 6 miles south of Johnston Island. However, due to a programming failure, it burst directly over the island at the desired elevation. Orange was launched at 2330 hours from Johnston Island on 12 August. It was detonated at an altitude of 141,000 feet, approximately 26 miles south of the island. At time of burst, middle clouds covered the island. Of the thermal effects studied on both Teak and Orange, emphasis was placed on 3 specific objectives. First, to record fireball size and growth. Second, to measure irradiance of the thermal pulse from 2,000 angstroms, far ultraviolet, to 120,000 angstroms, far infrared. Third, to determine the spectrum of the thermal pulse. Infrared studies on the size, duration, and spectral intensity of infrared emissions were made, with the immediate objective of providing input data for the designers of infrared guidance systems. For the measurement of thermal effects, the same aircraft stations and instrumentation as those on Yucca were used. The Teak fireball expanded very rapidly for the first 100 microseconds, reaching a diameter of 10 miles in 10 milliseconds. The Teak infrared fireball was almost 40 miles in diameter at h+1 second, after which it disappeared quickly. The Orange fireball expanded more slowly, reaching a diameter of approximately 1.5 miles in 10 milliseconds. The Orange infrared fireball, although of the same diameter, lasted somewhat longer than Teak. Teak produced a single thermal peak at about 500 microseconds, decaying to less than 25% of the peak value in about 10 milliseconds. The corresponding times for a sea level burst would be 2 seconds to second maximum, and 6 seconds for the pulse to decay to 25% of peak radiance. The rapid expansion of the early fireball was spectacularly different from a sea level shot. The lower orange shot showed a transition situation with the thermal pulse indicating some of the characteristics of a lower altitude shot, intermediate between teak and surface bursts. There were two peaks, the first of brief duration reaching a maximum at 500 microseconds, and the second consisting of a broad flat maximum lasting from 100 to 300 milliseconds. The spectra of orange consisted of a strong emission continuum with molecular band absorption superimposed. It was followed by molecular band emission beginning at the tail of the thermal pulse. Spectrographic analysis of teak, however, showed no observable continuum. Strong emission bands of excited nitrogen and oxygen were predominant. As a part of the thermal studies, a biomedical project examined the hazard of chorioretinal burns utilizing rabbits for the tests. Damage by thermal energy to the retina or to the choroid will leave permanent scars or lesions which will not result in impairment of vision, nor is pain associated with such burns. However, if the burn occurs on the macula, loss of central vision and visual acuity will result. The phenomenon of chorioretinal burn is distinct from that of flash blindness, which is the temporary loss of vision resulting from lesser amounts of thermal energy than that required to produce burns on the inner eye. For the teak shot, animal stations were located on Johnston Island, on aircraft and ships out to 300 nautical miles. Each station had instrumentation to record the thermal input, and cameras to record the visibility and the attitude of the rabbit's eyes at time of burst. For orange, there was no station on Johnston Island. The station farthest from the burst was an aircraft at 225 nautical miles at an altitude of 24,000 feet. On teak, chorioretinal burns were produced on all rabbits exposed, except on the surface ship at 300 miles, where clouds and ship roll may have prevented the rabbits from viewing the initial flash. On orange, cloud cover interfered with the surface stations, but burns were received in the aircraft at 225 miles. Retinal burn diameter consistently correlated with distance from burst zero. The lesions produced at all exposure stations within 160 nautical miles were of sufficient size and severity to result in permanent retinal damage or severe loss in visual acuity. Thus, theory is verified that megaton nuclear explosions at the altitudes tested produced chorioretinal burns at great distances as a result of the rapid rate at which the thermal energy is delivered. Most of the energy is delivered before the effective blink reflex time of 250 to 350 milliseconds for rabbits and 100 to 150 milliseconds for man. The teak and orange blast program obtained surface and near-surface air blast pressure time measurements. Instrumentation included standard pressure time and very low pressure self-recording gauges located on ground baffles, on 34-foot towers, and on ships backed up by electronic recording gauges. For both shots, the pressure values measured were considerably lower than predicted by conventional methods. On Johnston Island, at a slant range of 252,000 feet from shot teak, the overpressure measured approximately 0.1 pounds per square inch. The same station at a slant range of 196,000 feet from shot orange measured 0.18 pounds per square inch. The nuclear program objectives were to seek data first on neutron flux and energy versus range, and secondly, on gamma radiation. 3 of the 4 instrument pods attached to the missile contained time-dependent radiation detectors. Some of these provided neutron time of arrival data from which energy and flux could be determined. Others gave data on gamma radiation versus time, gamma dose, and gamma ray, as well as electromagnetic effects on equipment components. These pods telemetered data to a receiving station on Johnston Island. The fourth pod, programmed to be closest to the detonation, contained threshold foils to determine gross spectral and flux neutron data. This pod was to be recovered after exposure. The pods were ejected at appropriate times to place them at prescribed distances from the burst. Essentially, the desired data were obtained on both shots. Analysis of the neutron energy spectrum has not been completed. At 50,000 feet during TEAK, the gamma dose rate was about 300 milliroentgens per microsecond at 5 milliseconds. During orange, the gamma dose rates at 5 milliseconds were about 1,000 milliroentgens per microsecond at 30,000 feet slant range and 10 milliroentgens per microsecond at 100,000 feet. The gamma ray measurements were consistent between pods. Both the neutron and gamma ray data continues to be reduced and analyzed for application to the energy partition objective and for estimating the effective destruction range of enemy nuclear warheads at high altitudes. The ICBM structural materials pod deployed from the Redstone missile measured the weapon input and corresponding structural effects caused by exposure to very high altitude nuclear bursts, with particular emphasis on X-ray effects. Instrumentation included momentum reaction gauges, radiant energy intensity gauges, and ablation plugs. This pod required post-shot recovery. The TEAK pod was found intact. The orange pod was not recovered. The TEAK X-ray results showed large thermal X-ray-induced mechanical impulses of greater intensity than had been predicted. These impulses are capable of producing structural failures, as evidenced by the physical damage inflicted on the front instrument casing of the TEAK pod. There was no evidence to support the existence of an X-ray shadow, that is, a region of low intensity along the longitudinal axis of the TEAK device. The effects of X-ray-induced impulses on lead, zinc, iron, copper, and aluminum were appreciable at the estimated slant range of 23,000 feet from the burst. The effect on beryllium could not be measured. One of the most important studies in the high-altitude program concerned electromagnetic effects in the upper atmosphere. The possible use of nuclear weapons at high altitude as a defense against ballistic missiles requires that the effects of such bursts on electronic systems be determined. Information was needed to determine the performance of missile guidance systems, missile detection systems, and communication links in these and other situations. Electronic experimentation was conducted on the following effects: attenuation of electromagnetic signals, ionospheric disturbances, radar reflections or echoes, and noise emission. In probing the attenuation of electromagnetic signals, two distinct types of measurements were made. The first was over known propagation paths for frequencies ranging from 9 to 450 megacycles. The second type of measurement was the attenuation of cosmic noise. HF transmitters were located on Oahu, Kwajalein, Guam, and Christmas Island. VHF and UHF transmitters were in rockets fired above the burst. Receivers located on Johnston Island monitored transmission from the rockets, as well as the transmission from Oahu. Receivers on Oahu and in an aircraft monitored the transmissions from Kwajalein, Guam, and Christmas Island. These ionospheric communication links all showed a signal strength decrease immediately following the detonation. Cosmic noise receivers were located on Johnston Island, at French Frigate Shoals, and on Oahu. These receivers were operating in the 30, 60, and 120 megacycle bands. The normal nighttime ionosphere will give echoes from the F layer when probed with pulses in the frequency range of 1 to 25 megacycles. An ionospheric recorder examining these reflected pulses was located on Johnston Island, and another in an aircraft whose mobility could probe the extent of any ionospheric disturbance. Radar reflection from the burst were studied in the 10 to 10,000 megacycle range, using a variety of service equipment and 5 specially constructed sets. Radar sites were located aboard the motor vessel Acania, moored at Johnston Island, and in a specially instrumented aircraft. At 0 times, the aircraft was 225 miles from Teak and 125 miles from Orange. In addition, ANCPS-9 weather radars were located on Johnston Island and Maui Island, Hawaii. For shot Teak, the VHF radars aboard 2 destroyers at sea, approximately 75 and 150 nautical miles from Johnston Island, were utilized. These sets were not employed on shot Orange. Prior to burst time, radar echoes were being received from clouds, aircraft, and miscellaneous objects. Monitoring of noise emission in the 10 to 1,000 megacycle frequency range was conducted on equipment utilized for other studies. Additional instruments were provided to detect noise at frequencies of 31, 113, 10,000, and 35,000 megacycles. These additional instruments were located at Oahu, Johnston Island, and aboard an aircraft. A brief recapitulation of the findings in line with the general objectives sought from Teak, Orange, and Yucca shows first that high-altitude nuclear detonations are characterized by the rapid development of energy phenomena. The partition of this energy for Teak and Orange manifests itself quite differently from surface and lower air bursts. Much less force is transmitted by blast, while thermal and nuclear radiation are both more intense and extensive in area. Most spectacular was the extent of the fireball growth on Teak, the highest of the 3 shots, a diameter of 10 miles in 10 milliseconds, accompanied by a striking visual aurora. Teak produced a single peak thermal pulse, while the pulses of Orange and Yucca showed some of the characteristics of a lower altitude shot, intermediate between Teak and surface bursts. Chorioretinal burns on both Teak and Orange were produced over great distances as a result of the rapid rate of thermal energy delivery. This stems from the fact that the bulk of the energy is delivered before the blink reflex can operate. Extensive data on neutron flux and energy at various distances was successfully obtained. Although the 14 MeV flux data were not reduced in the field, preliminary study on lower energy fluxes indicated that they agreed to predicted values within 1 order of magnitude. The experimental data will serve to guide further theoretical development. The consistent gamma dose rate and dose data obtained with the pods give fundamental information on this radiation under the conditions of the new environment. The ICBM structural material study revealed the existence of large thermal X-ray-induced mechanical impulses of greater intensity than had been predicted. Samples of lead, zinc, iron, copper, and aluminum were appreciably affected. This closes the preliminary report on the effects of the 3 Pacific high-altitude shots. Since high-altitude effects form a comparatively new field of study with far-reaching significance, it must be emphasized that much more analysis of the HARDTACK data will be required before final evaluation of the observed phenomena can be made.